First, I want to thank the organizer for the invitation. And so, actually, I was thinking about what to talk about, and so today, actually, I decided to take this opportunity to tell you about 2D PT-invariant antiferromagnets. Okay, so I'm going to show you actually unpublished data on the deterministic, which is 180-degree domain switching, and the mechanism of the surface Dzyaloshinskii-Moriya interaction. Okay, so first let me thank my students and my collaborators. So I think most of the work was done by my former student Liang Wu, because it's a distinction work in magnetism, and now he's working on glasses in meta. He's still doing research, but on the optic side. And sample is actually from David Mandras, who is sitting in the audience. And we have theory collaborators from Charles King and Jim Lee at Penn, and also recently worked on Liang Blends and Renshan and their postdocs. I think 1/3 of my talk will be unpublished data, and 2/3 will be some early works. So since this audience is very diverse, I just want to tell you in one slide what other research direction that is working on in my lab. Actually, the majority of my group members are working on topology and quantum geometry. Like for example, we work on the topological crystal, and we collaborate with Yang Zhang in the early days to study the quantized CPGE. We also work on topological superconductors and on topological magnets. And now the chairman is also working on. And we also work on Kagome system with charged waves. Now let me go back to my talk, which is the 2D magnets. Okay, so I'll tell you that while we study 2D antiferromagnets, and especially I'm going to introduce the PT-invariant, the manganese system. Okay, and with new order. So then for the experimental part, I will show you nonlinear optics, but in the second order, to see the 180-degree domains. Actually, we can image 180-degree domain down to the monolayer, down to the bilayer in the sulfur compounds, and we also discovered recently that actually magnetic field itself can switch the 180-degree domains, and we propose the mechanism in the surface Dzyaloshinskii-Moriya interaction. So then for the selenium compound, we can image the 180-degree domain down to the monolayer limit, and we can also switch the neo vector by strain, and also the magnetic field. Okay, and I forgot to say that in my last slide, I will also talk something about machine learning. Okay, so yeah, let me tell you the motivation, which you probably have heard a lot. I mean, one of the motivation is about spintronics. Okay, so for example, this is a manganese phosphorus selenium 3, and these are two manganese sides with opposite spin with neo order. So if you do the red spin minus the blue spin, that's a neo vector. So these two states are related by Tanner-Russell operation. So basically, they have opposite neo vector direction. So green arrow is the neo vector. Okay, so this is like a binary memory state. And so the advantage of antiferromagnets is that at least in the collinear antiferromagnets, like in the neo order, there's no stray field, so it's very stable to external magnetic field. And the other thing is that usually in the antiferromagnets, the magnon frequency is in the Terra regime due to the large anisotropy and the large exchange field. So then that's an advantage. But the disadvantage is that there's no stray field. It's very difficult to detect the 180-degree domains and switch them. In the literature, lots of work with to switch the 90-degree or 60-degree, but not 180. Okay, I will show you some advantage we make in terms of 180-degree domain switching. So then the other motivation was really to study down to the monolayer limit to see whether we can discover some new order. We did discover some vestigial pneumatic order in the iron compound, but today, due to time, I will tell you that. Okay, I will tell you what we did in the monolayer limit in the selenium compound. So then. Right, now let me introduce a PT-invariant system. Okay, so first, let's forget the spin. So these are manganese side, but let's forget the spin. And this dot is actually, this point is actually invariant center. So invariant symmetry is that we go from R vector to minus R vector to see whether the crystal structure is invariant or not. Actually, it's invariant. In other words, the system like manganese, phosphorus, selenium 3, sulfur 3, and also the NBT, they are all central symmetric in the crystal. Okay, so when we forget the spin, but if you include a spin, so if you do inversion operation, you will get to this state. Okay, the neo vector in the opposite direction. So they break invariant symmetry. And if you do time reverse operation, you will also get to this state, which means they also break time reverse symmetry. But if you do P, then the T will go back. Okay, that's why the PT is a good symmetry. So it's a PT invariant. The selenium compound has in-plane spin, and the sulfur compound has almost out-of-plane spin, and the even layer NBT is similar. Okay, my talk will be focused on these due to the time limit. So then I will tell you actually how we use the second homogenization to image the 180 domains. Okay, down to the bilayer limit. But before that, let me tell you about the linear optics, like which you might be more familiar with a ferromagnet. So if we have a ferromagnet with out-of-plane moment, and if we shine linear light at normal incidence, so then in the reflection, the polarization plane will have a rotation, which is called curl rotation, named after John Curl. And in the transmission fashion, the polarization plane will also have a rotation, which is called a Faraday rotation, named after Michael Faraday. Okay. Of course, I want to say that so usually for collinear antiferromagnet, there's no net moment like Curry effect, Faraday effect doesn't work. But of course, there's a special magnetoelectric material with linear with a diagonal electric and a magnet coupling, you can have a Curry effect. That is because, like in the as a surface. Usually the surface electric field, and that surface electric field can induce a surface moment. Okay, but again, usually for a compensated antiferromagnet, Curry effect doesn't work. Okay, so that's why actually I want to show you actually the second homogenization actually work. But before that, let me tell you second homogenization because Peter talked about third homogenization, which has the same symmetry argument for the linear order, which is always allowed. The second order is different. Okay, so then this is the potential of the electron that fails. So then so this is second order. If you do if you change from x to minus x, it's invariant for the parabola, right? So that means it's essentially symmetric. But if you have a cubic term, then if you do u minus x, it's different. So in other words, if you have a non-central symmetric media, so the potential actually breaking for symmetry. So then this is the restoring force of the electron. So this is the spring force in the linear term, but then you also have the quadratic term from this cubic term. And this is F equal to ma. So the motion of the electron. So then this is the acceleration, and this is the these two are the restoring force. Okay. And this is a phenomenological damping term that is linear proportional to the velocity, but then one more force that is the light. So the light is driving the electron at frequency omega, maybe omega 1 in my notation. So then we solve this perturbation equation, then actually we can find out that the displacement of the electron in the second order actually can also oscillate at 2 omega 1 frequency. Okay. And this is the origin of the second homogenization. So if we shine omega light on crystal that break inverse symmetry, for example, DBO crystal, we get 2 omega out. So basically, red light in, blue light coming out. And in the quantum mechanics picture, as Peter already showed, so this is a real state, this is a virtual state. So basically, it annihilates 2 photons with frequency omega. They emit another photon with frequency 2 omega. So this is second homogenization. But in short, I mean, the most leading term is really we need to break inverse symmetry that allows the second homogenization. Okay, but that's not the full story of the second homogenization. So this is a Poynting vector for the source of the second homogenization. The first term is from the inverse symmetry breaking, the dipole term, but we can have higher order contributions, for example, from the lattice. Okay, from the lattice to quadrupole. So this is always allowing any system. It just whether it's small or not, it really depends on the material. Of course, you can also have magnetic dipole turn and in magnet materials, and this is usually dominant when the transition is resonant with a DD transition. Otherwise, it is rather weak. So now let's look at like the manganese compound that I'm going to show you, and also the chromium oxide, which was done by Fiebig in the early days. So this is the same as manganese, phosphorus, selenium 3. The crystal is centrosymmetric, but the spin break inverse symmetry. So then we'll have, for example, we can have two contributions. One is the spin, so spin immersion breaking turn with a dipole turn. Then we'll have a quadruple turn. So for the quadruple turn, if the spin is flipped by 1 degree, by the Taros operation, it's invariant. Okay. So then for the second order susceptibility, it's invariant when we flip the spin by 1 degree. But for the dipole turn, which is the chi-C turn here, which will change the sign when we flip the spin by 1 degree. So what we measure is the second E2 omega modular squared. So then you can see the intensity, there is the interference term between the 1 degree domain. So Fiebig basically started with this field, and he imaged the domain on ball crystal. And but what I show you is that we made some advancements in terms of sensitivity and also spatial resolution, that we can actually image the domains down to the monolayer, which this CCD technique didn't work.
Yeah. I have a dumb question. So an elementary question. So when you look at the second order response in a magnet,
Yes.
do we know the signal is coming from the electric field or coupled to the system, or the magnetic field coupled to the system, the spin? If it's magnetic field, then I think the symmetry always allow this second order.
Yeah. So okay. So I think you're talking about, so you can have like E, EB, like chi, E,
Or
H.
just the HH.
Yeah, you can also have that.
Right. So how do you distinguish? If you see a 2 omega signal, do we know it's an electric field, a 2 omega coming from the second order response of electric field?
You have to break T symmetry to see it in the second.
That's
Magnetic dipole.
That's really weak in the optical regime.
Yeah, usually it's much
I
weaker.
said which way?
Yeah. So in principle, like EH, HH, they are all allowed, but really high one. Okay, so
That's how you couple to magnets.
so then, yeah, so first let me talk about the sulfur compound. Yeah, in the literature, people call Heisenberg. But that's because if you measure susceptibility in in-plane, out-plane, you can see the overlap at high temperature. Sorry, I forgot to say that the Neal temperature is 78. Okay, Neal temperature is 78 Kelvin. But I mean, it's order, right? So it's not really a 2D Heisenberg model. That's because the 3D ordering comes from interplanar coupling. Okay. There are a few things that I want to emphasize. First is that right. I think the first thing I want to emphasize that so this material does not allow diagonal magneto-electric coupling. In other words, even if surface electric always exists, there's no surface moment out of plane. Okay, and no surface out of plane. So in other words, we actually didn't see any curve effect in the sample, and this will become important later in terms of the switching. So then, yeah, so then we do the measurement. You can see that we measure second half generation. So we're shining 1.55 EV and measuring 3.1 EV. So then you can see that we cool across the transition. You can see that actually we actually did 10 times. Okay, we did 10 times. Here I show you two curves. Basically, the 10 traces collapse into two or regroup into two. Then it's split at 78 Kelvin. This is a bulk sample. So this is actually basically the signature of the electric dipole term. So this ED is the same as the chi-C term. Okay, in the literature, some people call chi-C, some people call chi-ED, and some people also call it non-reciprocal second half duration. It's the same thing. So then, yeah. So why we see this phase transition? That's because the electric dipole term actually is proportional to the stack magnetization. In other words, this is a Neal vector. Okay, so that's order parameter, and you can see that here it actually go down first, because I told you that the electric dipole term will change sign. One is negative, another is positive. Okay, of course we measure modular square, so in the end it will go up. But anyway, so we define this point as a Neal temperature where the two traces split. Okay, and this is domain 1, domain 2. They're right here. So then I also want to explain the cross and parallel Because it will be important later for the selenium compound. So parallel means that we put polarizer. Laser point died, but I don't know. A better one. So we put a linear polarizer here, and here we make them parallel with each other. Then we rotate them 360 degrees. We call parallel. Okay, and we can also make the second harmonic beam perpendicular to the incident beam. We call crossed. We also rotate them 360 degrees together, and here they don't look different in the two domain, but only the magnitude. Again, this can be well understood by the magnetron group, which I will talk about. Then we did the mapping, and this is 15. Okay, also oh. So we did the mapping. So this is a 50 micron scale, and so this is an optical image which shows that the thickness is different, but you can see that what's surprising, the sample is in a single domain over like 300 maybe micron. Okay, then we want the sample above the near temperature and cool down. We can see two domains. Again, that's because we have a quadruple turn. We also have a dipole turn, and dipole then change sign when we flip the spin by 180 degrees. Okay, so then we do the same trick as the graphing that we learned from the graphing. So then in the two-layer limit, we can see the transition. Again, we define where the signal split as the nil temperature. Okay, so the nil temperature is pressed. That's because the fluctuation become more important in the bilayer limits. And we didn't see the order in the monolayer. It could be the Heisenberg model, but it could be disorder. So we don't know. So now let me show you the unexpected discovery in this compound, which is the one-digit domain switching by the magnetic field. Okay, because usually for magnetoelectrometer, you have to apply E and B. But we are applying B out of plane, in other words, parallel with E field, which is forbidden from the magnetron group symmetry. So here we basically measure second generation as a function of out of plane magnetic field. Okay, on the C star axis, you can see that. So this is a spin flop. Okay, so when the signal change here, this is spin flop, and we can actually see from the second generation. So at zero field, the spin is almost out of plane. It has 6 lobes, and at here it is 2 lobes. That's because the neo vector is in the plane. Okay, so this is not a surprise. The spin flop phase transition. What was surprising that we go up first. Sorry, fluids go up. Okay, we go up, then we go down. It didn't go back to the original state. You can see that the hysteresis loop, and this is always repeatable. And because we know the intensity at 65 Kelvin, well, because we do the thermal cycle, we actually know there are 1 domains. Okay, and also what you can see is that at this state and this state, like all of the sample actually switch the domain. This is different from the spectrometrics community. Thin films often the fraction of the sample is flipped, but here the whole sample flips domain. So this was a surprise because, yeah. So magnetoelectric coupling cannot explain this. So then we talked to our theory collaborators, and it actually took them quite some time to figure this out. That was because the Dzyaloshinskii-Moriya interaction is not allowed in the bulk, okay, because of the crystal is central symmetric. Then, but actually, it's a surface break invariant symmetry. In other words, in the bottom is the substrate, in the top is the vacuum. So then, so that break, the surface break invariant symmetry. So then, to still allow the D vector, still allow the D vector. Again, so in the monolayer, actually the D vector is along the mirror symmetry. Okay, it's along the 3 mirrors. So if we add all of the D together, it's at 0. But then in the bilayer, in the bulk, it's monoclinic, and this is monoclinic stack direction. So then if we have like 2 layers, like a D2 and a D3, we are rotate. So then in the end, there's a net delta D, okay, like in the bulk or in the bilayer. Then this is the energy. This is the energy of the system. So this is the exchange, right? This is the exchange, and this is the anisotropy turn. And EK means the ED axis, okay? And this is a Zeeman turn, and this is a new turn that actually breaks the degeneracy of the 180 domains, which was a surprise. So then, yeah, in the exchange limit, we can write down the energy. So N is the neo vector, okay? So N is the neo vector, and I already defined other terms. But anyway, so long story short is that at 0 field, the 1 degree domains is here, and there's a large barrier. So when we apply the magnetic field along the C-star direction, so the barrier between the 1 degree domain become less, and at some point the barrier disappears, so then it will slide into the other 1 degree domains in the other state. And we go back to the zero field, the barrier recovers, so then becomes stable in the other domain. Okay, in the other domain. But there's still something that we don't understand. So first of all, if you look at the spin flux field, when we increase the temperature, the spin flux field increase. Okay, but if you look at the hysteresis loop width, when we increase the temperature, when we increase the temperature, it actually decrease. In other words, the switching actually happens before the temperature dependent of the switching field is not related with the spin flux field. Now here you can actually see clearly. So this is spin flux field. This is a switching field. Okay, it actually switch before the spin flux field. Okay, so it's something actually we don't understand. So then the other thing is that we measured more than 10 samples. The switching always disappear below 62 Kelvin if the sample is around 40 nanometer to 80 nanometer. But if we measure a 4-layer sample, as you remember, the new temperature is suppressed, which means that anisotropy is actually reduced. So then actually we can see the switching down to like 5 or 10 Kelvin. Okay, I think we understand this. That's because the switching really depends on the delta D over K. Okay, when sample becomes thinner, the delta D is larger and the K is reduced due to the increase of fluctuation. So that's the part we understand. But now if you look at a thin sample, actually the switching field is almost identical to the spin flux field, which we don't understand. If you have any insight, please let me know. Then the other thing that we found is that actually, so this is one run, okay? Then we have other runs that we actually saw exchange bias. What do I mean is that, for example, if we repeat the measurement at 30 Kelvin, sometimes the switching field will be here, and sometimes switching field will be here. Okay, so it's this is what we call exchange bias. In other words, when we sweep up and sweep it down, the switching field is different. So this actually changed from different measurements. Okay, so this is another thing that we don't understand. We see exchange bias in the very thin sample. We never saw it in the 40 to 80 nanometers. We probably measure more than 10 samples, and this is repeatable. So now let me talk about the I have 7 minutes, right?
You have
Fifty-
about
I have
10, you
12,
have about 10,
yeah,
10, 12,
12.
12. What questions?
So then, so now let me talk about the selenium compound. Okay, so selenium compound, actually we were able to stabilize the long range order down to the monolayer. And so I explained the PT symmetries, and this is the data taken by David Mandris. So basically, this is the squid data. Okay, so the near temperature is 68, and this is second order duration on the ball crystal. So it agrees very well. As I told you that that's because the ED electric dipole susceptibility is proportional to the order parameter. Okay, so now let me show you that actually here actually data is not 0. Okay. As I told you, the quadruple term is always allowed, and the selenium compound is a rhombohedral. In other words, it's ABC stacking, so it has 3-fold within symmetry. So if you zoom out, maybe zoom in here and plot the polar pattern, actually the 3-fold symmetric. Okay, so then because this is we're measuring the lattice, but if you measure at 5 Kelvin or 10 Kelvin here, it's nothing like a 3 Kelvin. Okay, in the cross geometry, it's really like 2 lobes. That's because this is really dominated by the spin, okay? Because the neo vector is actually in the plane. It actually confirmed the spin flux story by the second order generation. Of course, the neutron also confirmed in the sulfur compound. Anyway, so long story short is that I hope you can remember that the nodal direction is the neo vector direction. Okay, this is something we determined by the magnetic point group symmetry. And also this was confirmed by DFT. Okay, and why there's asymmetry here? That's because the dipole term plus the quadruple term will give you some asymmetry. But anyway, again, the nodal direction in the electric dipole term is the new vector. So then Yeah, so in the literature, people call it XY magnet. That's because when they measure the spin stability, one of them is much larger than the other one. The other words, spin are really in the plane. Again, in the classical 2D XY model, there's no long range order, right? But again, so here is a 3D ordering from the interplanar coupling. However, if you consider the three-fold rotating symmetry plus time row symmetry, there will be 6 domains. Okay, and in the language of the Landau free energy, so this is called a six-state clock model. In other words, the ground state should have 6 domains, but that's not what we saw. Okay, so here is a 10 traces that I told you that we did in sulfur compound. We also did in the selenium compound. So we did 10 thermal cycle, but we only saw 2. Okay, and these are related polar pattern, and also we can do the centric for the for the domain imaging. So this is again 50 micron scale, and we do the imaging. Probably will polarize the light along here. So you can see that there are dark lines. Okay, so dark lines is actually domain wall, the 1 degree domain wall. Sometimes people call anti-phase domain wall, and the arrows are the neo vector. Okay, of course we don't know whether it's this way or that way, but we know they're opposite from the polar pattern. So then, if you warn the system about the temperature cool down, you can see the domain will actually move, and it really doesn't care whether the thickness is uniform or not. You're really kind of not pinged by these like thickness difference. Okay. So then, why the domain wall is darker? That's because the electric dipole turn is much larger, and around the domain wall, the electric dipole turn cancels, which leaves the quadruple turn, which is much smaller. Okay, so this is the 1 degree domains, and we can see that down to the monolayer. Okay, so this is the monolayer. Really, the monolayer, and again, the neo temperature is suppressed due to the increase of fluctuation. But as you know, in the textbook of 2D XY model, there should be no long range order. So that's another surprise. Okay, the first surprise that we saw 2 domains. Second surprise that we saw long range order in the monolayer limit. So. And anyway, so then we can do the same thing. Okay, we can image the 1 degree domains in the monolayer limit. The dashed line, the domain wall, the arrows are the neo vectors. So we warm up about neo temperature, then cool down. Okay, the domain will move. Okay, so why is that? So then I talked to my colleague. That was actually during COVID. I talked to my colleague Charlie Kim and Jim Lee, who are famous for topology, but they actually helped me a lot on the symmetry part as well. Because in graduate school, I was very busy working on topological material with Peter. I didn't learn much about symmetry actually, but I learned from them. So anyway, so when I talked to them, I asked them whether string can play an important role. But the first thing they asked me, how do you know string is important before they develop a theory? So then my student actually did a string tuning experiment. So here now the red arrow is a string. Okay, we use some polymer to apply string. It's not the neo vector anymore, but I told you that nodal direction is a neo vector. So we apply string horizontally, you can see that the neo vector is horizontal. If you apply string vertically, sorry, this is that thing out. If you apply string vertically, the neo vector is also vertical. If you apply string 45, neo vector is 45, and if you do minus 45, the neo vector they follow the string. Then they believe the string is important, and within 1 week, Charlie developed a Landau theory, Jean developed the microscope theory, but due to the time, I will show the Landau theory. So I told you that if the crystal has a 3-fold rotation symmetry, plus the time symmetry, there will be 6 states. Okay. And this is the neo vector magnitude. So then the 6-state plot model in the Landau free energy, the cosine 6 theta term. But if you have a string, then actually you have a 2 theta term. Okay, this term actually always dominates because it's a low order. So in other words, because of string, the system always pick 2 ground state out of 6. Then actually string can also stabilize the order in the monolayer limit. Okay, so that's how it works. Then in the selenium compound, we actually can see the 180-degree domain switching down to the monolayer, okay? Down to the monolayer. In other words, here we apply implement field, okay? We apply implement field. Again, the switching happened before spin flop because at right here, spin is going to flop. But anyway, so we saw the domain switching before the spin flop, and this is in the monolayer, and yeah, we can also see the like domain walls during imaging. But again, we don't understand actually the exchange bias. So here in this compound, we always see the exchange bias, whether it's like monolayer or like a 40 nanometer. So it's always there. Okay, that's something we don't understand. So let me summarize my talk. Okay, so in my talk, I show you that nonlinear optics in the second order actually is very useful to detect the long-range order in the PT-invariant system in the manganese compound. Manganese phosphorus sulfur 3 compound, we can see down to the bilayer for the long-range order. And the selenium compound, we can see down to the monolayer. Okay. And we can switch the domain by the stream, and we also discover that a magnetic field can switch the 180 domains. So in the sulfur compound, we propose in the surface Dzyaloshinskii-Moriya interaction. Selenium compound, it can be that, but it can also be the linear magnetoelectric coupling. Okay. So then I told you that in the sulfur compound, actually above the nil temperature, we discover new order in a very thin limit, which we call vestigial magnetic order, which I didn't have time to talk about. So as I promised in the beginning, I will tell you something. I will say something about machine learning. That's the last slide. Okay. Because I was, at least for me, and I'm very interested in PT-invariant antiferromagnet. Not just imaging the domain, okay? Because we can study like quantum geometry, for example. So then, in the early days, I asked one of the leaders for the Bilbao data server. I won't name the name, but I asked him or her send me a list of a PT-invariant topological antiferromagnet, and I got a list of 30. Okay. Then I asked my postdoc, I think, why don't we check everyone in the literature? But none of them was PT-invariant. In other words, the Bilbao, in my opinion, okay, from the Bilbao database is not very reliable for the magnet materials. But I don't know whether machine learning can help, but I hope, for me, again, if you can send me a reliable list for the PT-invariant antiferromagnet, whether it's a topological or non-topological, I will appreciate. But I think for the community, a more reliable magnet database is needed. Maybe other methods can help, and thanks for attention.
Any questions?
So I remember you showed the temperature dependent susceptibility of, I think, the latter material, and which was showing large anisotropy at large. Yeah, that one. Yeah,
Which one?
you just this one.
Yeah.
At temperatures well above the ordering, and you were saying that's an evidence of XY or something. I mean, why would that be? Why would that not just be some anisotropy in G factor?
Well, again, so that's what this paper says. But anyway, so this is basically the evidence that spin are in the plane.
No, magnetic moments are in the plane. Where spins are, we don't know. G factor can be anisotropic. What we measure are magnetic moments, not spin. Magnetic moment is related to spin with the G factor. If G factor is strongly anisotropic, spins can be isotropic, but magnetic moments not.
Yeah, okay, sorry. So this is actually a theory paper. So they basically look at specific susceptibility data.
This is not a
neutron
spin
scattering.
susceptibility, it's magnetic susceptibility.
Yeah.
So it's spin susceptibility multiplied by G tensor. I mean, what I'm just saying is that from magnetic susceptibility, you do not necessarily infer spin susceptibility.
Okay, anyway, I'm happy to learn from you about this. What I want to say is that in the literature, so they basically look at neutron scattering plus these data, and they say the XY, but
Okay.
yeah. That's what we'll quote here.
Are there any other questions? Then we can move on to the next talk.